In this question, a fictional scientist is investigating a reversible reaction between fictional substances Ge3, G, and E2 at a temperature of 330 Kelvin and at a pressure of 1 atmosphere. So here we've got our equation. Again, we're seeing that reversible arrow showing this reaction can happen forwards and backwards. We're also told the enthalpy change of reaction is 1,640 kilojoules per mole of reaction. That's telling us, since we have a positive enthalpy change of reaction, our reaction is endothermic, meaning it takes in energy. We're going to start by writing an expression for the reaction quotient Q for this reaction. Here's our reaction quotient equation. It's exactly the same as we've been using so far on this skill. So we've got our concentrations of our products in the numerator to the power of their coefficients. In the denominator, we have the concentrations of our reactants to the power of their coefficients. Remember, only gases and solutions are included in the equation, not solids and liquids. So in our products here, we've got G, but it's a liquid. Because it's a liquid, it's not going to be included in our equation. Then we've got E2, that's a gas. So we've got concentration of E2 on top of our fraction to the power of its coefficient, which is 3. On the bottom of our equation, we've got Ge3, which is a gas. Great, that can be included. And it's got a coefficient of 2, so it's going to be squared. So we can go ahead and fill that in. On the top, we have E2 cubed. On the bottom, we have Ge3 squared. Okay, so now we're going to go through looking at this table and determine and explain how the system would respond to each of the following stresses. So the first stress that happens is that some Ge3 is removed. So our job is to figure out how would this affect Q and K, and therefore how would the equilibrium shift. If some Ge3 is removed, looking at our reaction quotient equation, here's Ge3. If some Ge3 is moved, the concentration of Ge3 is going to decrease. So the thing on the bottom of my fraction is going to decrease. If the thing on the bottom of my fraction decreases, as a result, Q is going to increase. So the effect on Q here is that Q is going to increase. We're also asked about an effect on K. Now, the only thing that can affect K is temperature. So changing how much G3 we have doesn't affect K itself, it just affects Q. So the effect on K is going to be no change. So we've had no effect on K, but Q has increased. So now we need to compare Q and K. Now originally, this system was at equilibrium. So now Q is going to be greater than K. So Q being greater than K, we can see from our reaction quotient, means that we have more products and less reactants than we need to be at equilibrium. So according to that, we're going to need to reduce the amount of products and increase the amount of reactants so that our Q value can decrease to get us to equilibrium. So in order for that to happen, our reaction is going to have to proceed in the backwards direction towards the reactants. So which way will the equilibrium shift? It's going to shift towards the reactants. What about if the container volume is decreased? So if we decrease the volume of the container, that means we're going to increase the pressure in the container. And increasing the pressure of our gases means we're increasing their concentration. So this part is only going to affect our gases in our equation. So E2, that's a gas. And Ge3, that's also a gas. So we know that the concentration of E2 is going to increase as the pressure increases, and the concentration of Ge3 is going to increase as the pressure increases. However, if we look at our Q equation, we can see E2 is to the power of 3, whereas Ge3 is just to the power of 2. So by increasing the concentrations of both of those by the same proportion, the top part of the fraction is going to get a lot bigger, and the bottom part of the fraction is only going to get slightly bigger. So overall, Q is going to get bigger. That's because we've got to the power of 3 on the top of our fraction. So the increase there is going to be bigger overall than the increase on the bottom. So our effect on Q is that Q has increased. That's because we had more moles of gas on the top of our fraction than on the bottom. Our effect on K, there's no effect on K here, only the temperature is going to affect K. So how does Q compare with K now? Q again has increased. We were originally at equilibrium. So that means Q is now going to be greater than K. Again, that means we're going to shift towards the reactants. And that makes sense because that's shifting to the side of the reaction that has fewer moles of gas. So that means that looking at our reaction here, if we're getting more in our reactants and less in our products, that's going to decrease our Q value so that it comes down to eventually equal K when we'll be at equilibrium. Our final stressor is that the temperature is increased. Now, the increase in temperature is going to affect K. It's going to have a different effect on K depending on if our reaction is endothermic or exothermic. If our reaction is endothermic, then increasing the temperature is going to result in an increase in the equilibrium constant. However, if the reaction is exothermic, we're going to have the opposite thing happening. If the temperature increases, the equilibrium constant is going to decrease. Now, this makes sense based on what we already know that we practiced before. If we have an endothermic reaction and we increase the temperature, we're going to want to favor that endothermic reaction so that some of that heat will be absorbed by the reaction taking place and lower that temperature again, according to Le Chatelier's principle. So that's why increasing the temperature increases K for an endothermic reaction, and the opposite reasoning is true for why increasing the temperature decreases K for an exothermic reaction. Changing the temperature, however, does not affect Q. The only thing that affects Q is the concentrations of our reactants and products, and changing the temperature doesn't change either of those immediately. So the effect on Q is that there's no change, there's no effect. What about the effect on K? Well, we have an endothermic reaction, and our temperature has increased, so as a result, our K is also going to increase. So now my Q stayed the same, but my K increased. We were originally at equilibrium, meaning Q was equal to K. Now K's increased. That means K is now going to have to be greater than our Q. So because K is greater than Q, now we need Q to increase in order for it to eventually equal K. So that means we're going to need the reaction to go towards the products so that we can generate more product and less reactant. That means that in our equation, the top part, the products, is going to get bigger. The bottom part, the reactants, is going to get smaller. Overall, that means Q is going to increase until it reaches K, the equilibrium constant. So this question gets us to those same conclusions as when we did just the Le Chatelier's principle questions without Q and K. This time, we're now able to use Q and K to explain why we have those equilibrium shifts happening. So for every stressor that we have, we're first thinking, how does this affect Q? Things that affect Q are things that affect the concentrations of things in our reaction quotient equation. So if our concentration of one of those is changed, that means Q is going to change. If our container volume changes, our pressure is going to change, and therefore the concentrations of any gases are going to change. So if we have any gases in our Q equation, changing the container volume is going to change their concentration and therefore change Q. Changing the temperature does not affect Q. Next, we'll think about the effect on K. The only thing that affects K here is our temperature change. If we have an endothermic reaction, then increasing temperature will increase K, or decreasing temperature will decrease K. If we have an exothermic reaction, increasing temperature will decrease K, and decreasing temperature will increase K. Finally, we're going to compare Q and K. And if Q is greater than K, our equilibrium is going to shift towards the reactants. If Q is less than K, our equilibrium is going to shift towards the products.